Welcome back to this second half of the first lecture on Hamiltonian mechanics. The background for this lecture is a place called Yamashita Park in Yokohama, which a lot of people go to Tokyo and they never really get to because they kind of get lost in Tokyo. Yokohama is about an hour, maybe 45 minutes if you get a fast train west round the bay from Tokyo. And it's well worth a weekend or even a few days to explore. On a nice sunny day, there's a really nice long waterfront section that you can walk along, and this park is along that waterfront. It also has a really enormous Chinatown district that's actually quite fun to have a look through. Lots of nice temples and places to eat and drink and so forth. And then Yokohama itself is one of those cities that's sort of gentrifying in certain parts, and so if you wander through some of the older parts of town, you'll find like new hip little izakayas and shops and restaurants and bars and stuff. So it's well worth a look, and probably even just a whole weekend or a few days as a way to get away from Tokyo. What I want to do in the second half of this lecture is the first half was actually quite abstract, right? What we did was really drill in deep onto what a Legendre transform is and how it works with respect to two completely arbitrary functions, f and g, and completely arbitrary variable sets, u, v, and w. And that won't make a lot of sense in terms of context of Lagrangian and Hamiltonian methods. At that point, what I want to do in this half is actually join that up. So where I want to start is by applying a Legendre transform to the Lagrangian. And now that we've done all the hard work in the first half, we can apply that fairly quickly to getting where we want to go. What I'm going to do after that is demonstrate that the Hamiltonian H actually has a physical meaning, which is the total energy, and that's conserved. And then as the last step in this, what I'm going to do is look at doing Legendre transform for an actual real Lagrangian, as opposed to just the Lagrangian as a function, just to show you how it behaves between the Lagrangian and the Hamiltonian as functions, so that in particular you can see where the minus sign pops out in this thing as well. Okay, so let's bring up some slides. Where we're going to start here is by doing a Legendre transform on a Lagrangian, and you'll remember on the first half of the lecture we saw a function that looks like this, that at that point would have looked completely arbitrary, but now actually probably doesn't, because you can see that what this thing is really is just a Legendre transform. So let's work through a Legendre transform for the Lagrangian, but mostly by reusing the results that we got in the first half of this lecture. So I'm going to need some paper for this. If we consider where we're starting, we're going to have some function L, and now it's going to have a set of variables q1 through to qn, q1 dot through to qn dot, and possibly time t. And we'll include time t just to be fully general across the whole thing. Sometimes the Lagrangian's not dependent on time and you can leave it out. What we're wanting to do is come across to a new function that we're going to have in here called the Hamiltonian H, and it's going to have a set of variables in here, q1 through to qn, p1 through to pn, and the time t as well, okay? And so the place to start here is to remember what are our active variables and what are our passive variables, okay? So if we consider this thing here in terms of the context of f in the first half of the lecture, and this thing here in the context of g in the first half of the lecture, then what we're doing is we've got an active set of variables here that we want to change, u, or our u's, that are going to be q1 dot through to qn dot. And we want them to change into the v's for our function g, which is going to be p1 through to pn. And then the set of variables that we have that are our passive variables, which are w, they're conserved across the two, right? So the w for this set here will be q1 through to qn and the time. And in this set here, it will be Q1 through to Qn and the time, okay? And so you'll notice if you go back to the first half of this lecture that I was very careful to make sure that my active set, U and V, went from 1 to N, and my passive set went from 1 to M, where M is not equal to N. That's because in this particular case, N, the lengths of the sets are different, right? Here, our active set has N variables, and our passive set has N plus 1 variables. And if I didn't define my Legendre transform to work for different sizes of sets, I'd be in a little bit of trouble here, okay? So there was a little bit of foresight, making sure that everything's going to behave over there. So the first step of the Legendre transform is to define your new variables, right? And you'll remember what we did was we wrote something along the lines of our VI is equal to df on dui. And without going through and doing all the algebra again, we can just pull the results so we know just by substituting in what the variables are for what they were in the algebra that we did. This would now be Pi is equal to dl on dqi. If we just go back and map from our functions to our functions, our variables to our variables, okay? And this of course is a thing that we already had defined. This is just our canonical momentum. So that pops out quite nicely here, okay? We also had earlier our way of defining G in terms of our function f, and it was basically the sum from I equals 1 to n of ui vi minus f. And so if we now map that across, our function h is going to be equal to the sum I equals 1 to n of our u's are our q's, q dots, so this will be qi dot. Our v's will be p's, so pi, minus our function that replaces f, which is the Lagrangian. And of course, p and q in here are just numbers, so we can reverse their order. And so this thing ends up being sum I equals 1 to n of pi qi dot minus L. Okay, and so that's basically how we get this expression up here. All we're doing is just defining H as the Legendre transform of L, where we change the Q dot coordinates to the P coordinates. That's all that equation is. It's just do a Legendre transform. One thing that you'll notice that we got out when we did our Legendre transform earlier is that UI is equal to dg on dvi, right? You'll remember if we pop back up, we had this nice symmetry that runs from our input side to our output side, and sort of nice symmetry of results in here. So we can consider that symmetry of results. And so if we run this across, what this now is going to be here is our u's, and our u's are q dots. So this would now be qi dot is going to be equal to the derivative of our new function, dh, on the variable for our new function, which is going to be dpi. And so we've got a new little equation that pops up in here, something we haven't seen before. Okay, so we haven't defined this because we haven't had a Hamiltonian and we haven't really done anything with our generalized momenta, but that gives us the sort of corresponding symmetric coordinate in there. And there's another thing that popped out from what we did earlier, which is that what happens for our passive variable set, right? So you'll remember that we had dg on dwi is equal to minus df on dwi. Okay, we got that back up here. So if we come down here and apply that, what we're going to find is that our dh on... Oh, actually, let's do this the other way around, because it doesn't really matter which way you write this thing. Okay, you could equivalently write this as df on dwi is equal to minus dg on dwi, and it gets us the form that is more familiar that you'll see in books. Okay, so in here what we would have is dl on d, our passive variables are the qi's, So this will be equal to minus dH on dqi. And you'll notice you could put the minus sign on either side, so it doesn't really matter which way around you write this. But the more conventional way to see it is as we've got written here. And our passive variable set doesn't just include the QIs, it includes time as well. So there's a second one that we would write in here, which is dl on dt is equal to minus dh on dt as well. And again, the minus side could flip to the other side, so you can write this either way that you want, okay? And then the last one to write here, it's less useful, but we'll write it because we know that it exists, is you'll remember that we could actually write the Legendre transform in its symmetric version as well. So you'd have f is equal to the sum I equals 1 to n of, this is going to be u's and v's, ui vi minus g. Okay, so you remember that was up in this table here where we looked at the symmetry. So this thing is now going to give us the old function L is going to be equal to the sum I equals 1 to n of P I Q I dot, for the same reason I can put them either way around as I said before, minus H in here. Okay, and so if we have a look at this all on one screen now, you can see that we basically just take the Lagrangian as our function f, the Hamiltonian is our function h, our passive variable set as the coordinates q, I, and t, our active variable sets as the qi dots and the p's. We do a Legendre transform and out pop a whole pile of useful relations in here. And we'll see that we can break them up into two symmetric sets, okay? So the first set is the ones that come from the active variable sets. And the first one is one we're familiar with. It's the definition for our canonical momentum. Pi is equal to dl on dqi dot. We get a corresponding relationship that defines our generalized velocity in terms of the canonical momentum now, right? Which is qi dot is equal to dh on dpi. And so if you want to go from the coordinates and velocities space to the coordinates and momentum space, you basically have to implement a whole pile of these transfers of variables across by using your L or your H to switch between the two systems. Okay, so suppose you set up your system and you decide to go down the Lagrangian approach and you find, well, actually it's not working. I really wish I had 2n first order DEs instead of n second order DEs. All you have to do is do the variable mapping across to the Hamiltonian form, and then you can just continue on down the road using the Hamiltonian form instead. Okay, so you can switch between the two using these relationships. And then from our passive variable set, what we end up with is basically a relationship between the Lagrangian and the Hamiltonian in terms of the passive spatial variables, which is the generalized coordinates, or time if there's a time dependence to that. And if there's no time dependence to that, you'll notice that all this really says is that 0 is equal to 0. Okay, works out quite simply. The one thing we're missing at this point is the Euler-Lagrange equations. Okay, so let's try and pick those up using what we've just learned about our Legendre transform. So Euler-Lagrange equations, what we would have is d on dt of dl on dqi dot equals dl, sorry, make this a partial. And it's very important that this is a partial. dl on dqi. Okay, so let's call this equation 3 for the moment, just to keep track of it. Earlier on, I probably would have, just to compare with my other notes, I would have called this one 1, and I would have called this one 2. Okay, just in case people are trying to map this to my handwritten notes. What we can do in here is we can use our PI that we just got up here, so we can use 1 to do the following. We know that PI is equal to dl on dqi dot, and let me put the dot in the right place. We can write pi dot, and our pi dot will be equal to d on dt of dl on dq dot I, like so. Okay, so all I've done is just taken the time derivative of this thing number 1, but of course we know via equation 3 that this is just equal to dl on dqi. Okay, so this thing comes via equation 1, this thing comes via equation 3 just here. And we know from just up above that our dl on dqi, so this term just here, is equal to dh on minus dh on dqi, right? So this thing here will be equal to minus dh on dqi. And so what we basically have here is pi is equal to minus dh on dqi as a result just in here. Okay. Now we know also that h is going to be a function of pi, right? Because we can look at it right back up here. H is going to be a function of pi somewhere in here, and so what we would naturally expect in here is that what about dh on dpi? And we know that we already have that. We already have that just here as equation 2, right? dh on dpi is equal to qi dot. So what we can come down here and do is write dh on dpi is qi dot. And just to make the symmetry in this really obvious to you, what we've got is as a final outcome is pi dot is equal to minus dh on dqi, and we have qi dot is equal to dh on dpi. And so what we have here is essentially two equations of motion, and these are what we know as Hamilton's equations of motion. Okay, so for each I, what we're going to get is two first order dEs from two derivatives of h, and we can compare and contrast that with Lagrangian, where what we had was two derivatives with respect to the two derivatives of our Lagrangian with respect to the two variables that we had, right? So dl on dqi and dl on dqi dot. And of course, those two are related directly to each other via the Euler-Lagrange equation. And so what we have here is for each I, we get one second order dE from two derivatives of L. And so this is ultimately our really key difference between the Lagrangian approach and the Hamiltonian approach. In a Lagrangian approach, what we have is basically our Euler-Lagrange equation, which takes our derivative of the Lagrangian with respect to the two variable types, q and q dot, and combines that into one second order dE. And in the Hamiltonian approach, we have our derivative of the Hamiltonian with respect to our two coordinate types, which is q and p. And instead of becoming one second-order differential equation, those become two first-order differential equations, and that's where you get this really useful difference between the Lagrangian approach and the Hamiltonian approach. You go from one second-order equation to two first-order equations. And that's really nice because when you're dealing with problems that are not analytically solvable and you have to work numerically or computationally, there's a very big computational advantage to handling first-order DEs because they're a bit more stable for numerical algorithms for solving DEs. Okay, so that kind of brings us round to what we would call Hamilton's equations of motion, which would be the equivalent of the Euler-Lagrange equation, and would use in problem solving later on. Okay, I'm not going to do a problem with Hamiltonian's equations in this half of the lecture. In the next lecture that we come along to, what I'll do is I'll do a couple of Hamiltonian problems, and we'll see this in use the same way that we've seen the Euler-Lagrange equation in use to get equations of motion into problems. So stay tuned to the next lecture for that one. Where I want to go with this next is to look at the physical significance of the Hamiltonian while we're dealing with just theoretical aspects of this new approach that we've brought together. And so what I'm going to do is step away from what we've just been doing with Legendre transforms and just deal with the Hamiltonian as a function on its own. So we have our function h, which is a function of q1 through to qn, p1 through to pn, and t. And if we want the derivative for this with respect to time, we know from several variable calculus that we need to write it as the sum of all of the derivatives, partial derivatives of all the variables that make up that function. Okay, so we've got dh on dt will be equal to partial derivative of dh with respect to dt plus the sum from I equals 1 to n of dh on dqi on dt plus the sum n I equals 1 of dh on dpi on dt, like so. Okay, so same idea as we had before when we were talking about df with respect to x and y. You've got you know, your partial derivative along x, your partial derivative along y. You add those two things together to get your thing. And here we've got a multivariable space. Okay, so what we're going to do here is start playing around with the right-hand side of this. So we've got dh on dt plus, we can pull the sum out to the front because it's the sum over the same number of variables in both cases, right? For every qi, there is a pi, and so the two sets have the same length in this particular case. So this is I equals 1 to n of d h on dqi. dqi on dt is just qi dot, right? So this is qi dot just here, plus dh on dpi times dpi on dt, which is just going to be pi dot. And you'll know that you'll remember that just up earlier we dealt with a pi dot, right? In getting our Hamilton's equations of motion. So the next line in here is going to be dh on dt plus, keep this sum. We can now use our Hamilton's equations of motion, which we just had up here, to clean up our qi dot and our pi dot, right? So we're going to have dh on dqi. Our qi dot is going to be dh on dpi. So dh on dpi. Our pi dot is going to become minus dh on dqi. So we're going to have a minus sign here in the middle. And so this is going to be dh on dpi, dh on dqi. And of course, these two derivatives are interchangeable, right? So these two terms that we're now taking the difference between are exactly the same. So they all cancel out all the way through. And what we're left with is just dH on dt. So what we find in here is that the time derivative of the Hamiltonian can only really come about because of a dependence explicitly of the Hamiltonian on time. So if the Hamiltonian has no explicit dependence on time, that means that dH on dt, the partial derivative, will be equal to 0. And of course, that then means that dH on dt is equal to 0. And if that's constant, what that means is that h is conserved. And so whatever h ends up being connected to, and in a moment we'll see that it's actually connected to the total energy for the system, and you'll totally expect that because you'll go from L equals T minus V to H equals T plus V when you do your Legendre transform. What we're saying is in the Hamiltonian problems, if the Hamiltonian has no explicit time dependence, then the Hamiltonian is conserved. The Hamiltonian is connected to the total energy of the system. And so any Hamiltonian that has no time dependence is really just stating that you have conservation of energy. All right? So this is the other nice thing about the Hamiltonian approach compared to the Lagrangian approach. It is that the Hamiltonian approach, the function that you use as part of that approach, the Hamiltonian, has an actual simple physical meaning. It is just the total energy of the system. And if the Hamiltonian has no time dependence, then the total energy of that system is conserved. Fairly simple, okay? So let's finish off here with a really simple example because, I mean, we've sort of worked our way from very abstract Legendre transforms through to slightly less abstract where we've been working on Legendre transforms of functions. And now I want to bring this down to an actual real problem just so that we can see how this all fits together, okay? And so what I'm going to do is do a Legendre transform on a fairly simple Lagrangian just to show you that everything behaves itself quite well. So let me just pop in here and define a problem that looks a little bit like this. We've got a tennis ball, and the tennis ball is at some height y above ground, which enables us to define our gravitational potential energy quite well. It's at a particular time traveling to the right with velocity x dot, and as we know, eventually gravity will catch this thing and it'll fall down, but we're going to deal with t equals 0 and just work out what happens with defining our Lagrangian and then converting that into a Hamiltonian using a Legendre transform, okay? So as you know, there's 2 degrees of freedom in here. There's motion to the motion in the direction x and motion in the direction y. And that means that there's going to be 4 coordinates for our Lagrangian version of this. There'll be x, y, x dot, and y dot, okay? Generalized coordinates, the first 2, generalized velocities in the second 2. To get our Lagrangian, we need 2 things. We need the kinetic energy and the potential energy. The kinetic energy here is pretty easy. It's just the half mv squared, and v is just our x dot. So this will be a half mx dot squared. And our potential energy is going to be entirely just the gravitational component here. And it's going to be given by mass times gravity times the height above whatever our reference level is for our gravitational system, which we've set our 0 just here for this. So it's now going to be mgy. And of course, then what we would do is get our Lagrangian. Our Lagrangian is basically t minus u. So this thing will be a half mx dot squared minus mgy. Okay? You'll have all done this pretty comprehensively over the last few weeks, including for more complicated problems in this, so it's fairly easy to get. So what I'm going to do now is actually do a Legendre transform on that Lagrangian that we just took to get to the Hamiltonian. So let's pull this out. Our H is going to be sum from I equals 1 to n of P I Q I dot minus L, okay? And the hard part of doing this transform always is dealing with this sum term in the front, right? Because you need to, if you've got one variable, it's really easy. If you've got n variables, you've got this great big sum that you've got to work through to get from one to the other, okay? And I'll see if I can come up with some tutorial questions where you've got slightly better problems where you need to go from one to the other with a Legendre transform, so that those of you who want to try it can have a little bit of fun with it. So what we're going to do is deal with our PI, QI dot terms in here, okay? And in particular, what we know is that we have PI is equal to DL on DQI dot. That's just the definition of canonical momentum. And we also know that QI dot is going to be equal to essentially the derivative of QI with respect to time. Okay, so if we're working on our dPi dQi in this particular case, it's going to be, we have one variable we have to deal with in the x direction, and we have one variable that we have to deal with in the y direction, right? Because there's an x and an x dot, and that x dot would have a corresponding px, and there's a y and a y dot, and that y dot will have a corresponding py. Okay, so there's going to be two terms in here, and we can basically write this as pi, so this will be dl on dx dot times qi. Actually, let me just put one more step in here. I will do it. So this would be pxqx dot plus pyqy dot, just to make it really clear what I'm doing, okay? So where we would go in here is that this is going to be, let me just scroll back because I want to use those definitions above. dl on dx dot, so this is really just now taking my pi up here and putting in my x dot into it. I'm going to have my qi dot in here, which will be this one. Okay, so this would now be dx on dt. Okay, so px qx dot is going to be dl on dx dot dx on dt plus dl on dy dot dy on dt in this particular case. Okay, so I'm not doing chain rule here. You'll notice that it's x dot on the bottom and x on the top, and not x dot or x and x. What I'm actually doing is doing px times qx dot, and those are dl on dx dot and dx on dt. Okay, so this is not chain rule. What I need to do now is look back up to where my Lagrangian was, because I need to do some derivatives, right? I need to do dl on dx dot, and dl on dx dot, if I look back up here to my Lagrangian, I'm going to get a 2 down from the x dot squared, so this is going to be mx dot. And then dx on dt is just x dot, right? So this is going to be times x dot plus dl on dy dot. What I need to do is now take the derivative of L with respect to Y dot. And as you know, there's no Y dot terms in that term up there. So it's going to be 0 times dy on dt, which will be y dot, okay? And you'll notice that 0 times y dot is going to kill itself off. So that leaves me with mx dot squared just in here. And of course, now we can finish off our Legendre transform in here. So h is going to be mx dot squared. That's my sum pi qi dot minus my Lagrangian. So this is now going to be a half mx dot squared minus mgy. Okay, so just to make this really clear, what I've done just down in this line here is taken h at the front minus what comes out of this sum pi qi dot and subtracted my Lagrangian function from the back of it with my Lagrangian function just being here. Okay. If I now go down and do this, this is going to be mx dot squared minus a half mx dot squared plus mgy. Okay, same as I did when I did that example in the first half of a random function, you know, u squared plus w with my Legendre transform. And then, of course, mx dot squared minus a half mx dot squared is a half mx dot squared plus mgy. And now I've got my Hamiltonian, okay? And you'll notice that this thing is, if we consider back up what our kinetic energy was and what our potential energy was, this thing is now the kinetic energy plus the potential energy is equal to the total energy. And so you can see the functional form that pops out for this, right? And you can also see in this why you get the change in sign in the potential energy between the Lagrangian and the Hamiltonian comes about as a side effect of the Legendre transform, which is a side effect of switching from generalized velocities as your variables to generalized momenta as your variables. And I guess that brings us kind of to a nice place at the end of this lecture. I'll do some examples in the following lecture, but just to round this out, now what we've seen is historically you go Newton's method, don't have good maths, have good maths, all of a sudden we've got Lagrange's methods, we've got enough calculus now, so you've got Newton's method with a calculus upgrade. Another 100 years of maths being developed, and then you get Hamilton's approach, which now has the added advantage that the function you deal with, which is the Hamiltonian, has a physical meaning, it's the total energy, and your equations pop out as two first order DEs instead of one second order DE. The reason it came out that way is somewhat historical, right? This got discovered, then this got discovered. But you could imagine that, you know, perhaps had history played out very, very differently, you might have just gone directly from Newton's approach to Hamilton's approach, and then someone might have worked out, hey, you can do this Legendre transform to get back from Hamilton's approach to Lagrange's approach, and there you would be giving up the Hamiltonian having a meaning. You no longer have it as a total energy, it's just something else that you do a convenient transform on, so that now you can instead deal with coordinates that are momenta and position and velocity rather than position and momentum. And the nice feature that you get there is instead of 2n equations that you have to solve, you have n equations that you have to solve, and they actually look like F equals ma directly rather than like two little separate first order DEs, okay? And this is the thing that you'll realize when we get to the next lecture that you lose in getting to the Hamiltonian approach, which is that the equation that you use at the end no longer really looks like Newton's second law. The Euler-Lagrange equation very much looks like Newton's second law, and that makes it a really nice connection upwards to your Newtonian mechanics. Anyway, I think that's the best place to stop for this lecture because we've kind of come all the way through the theoretical constructs for dealing with Hamiltonian systems, and in the next lecture I'll give some examples of how to use a Hamiltonian approach directly to problem solving, and we'll also spend some time looking at a really interesting feature of the Hamiltonian approach, which is a thing called Poisson brackets, which has some really important connections to quantum mechanics, and it's the main reason why it often gets very strongly pointed out in classical mechanics courses. I'll see you next time.